So I was already introduced. This is some of the things I did. Very long time ago, I started hacking at Hectic. You may remember that. It's a bit, can you read it? Oh yeah, it's big enough, right? Yeah. Wij vertrouwen stemcomputers niet, de XA developers. Well, as you just said, I was reverse engineering things for a very long time already when I was young. Unfortunately for my mother, I took apart her sewing machine at some point when I was 3 years old. So this, I was never satisfied until I know how something works inside. Now I'm going to talk about the Pixel phone. There's a TitanM2 security chip in that. Why is that an interesting chip? Well, it manages all the security of the phone. Your PIN entry, all the secure keys that are stored in the phone, they're all managed by this chip. So I want to understand how it works, and therefore I need to look at the firmware. First I looked into this Titan. The word Titan happens a lot in Google products. Originally this chip was developed for data centers to secure the Google Cloud services. Then the very old Pixel phones, they had a different security chip called from NXP, just a different manufacturer. Then with the Pixel 3, they started with an ARM-based chip, which was called TitanM. For the newer, starting with the Pixel 6, it's the M2, which is a RISC-V based chip. There are many other things, so this is better to read it. Oh yeah, I'm not a graphics designer, as you may see from my slides. There is no relation to the submarine. There's a project called OpenTitan, which has a very similar functionality, but it's open design and is not from Google itself, so it's a different one. And then I just saw yesterday, or today, was it? Today, from Tropic Square, there was also a talk about the secure element, and that's also another open project with the entire chip as open hardware, not related to the Google chip. There's a Google dongle where you can store passwords on the USB stick, also not related to this Titan chip. And then just last month there was another project from Google called Titans AI, and also completely not even security related. So this word Titan happens a lot. There's the first version of the Titan chip that was in the phones for the Pixel 3 until 5, introduced in 2018. That was an ARM-based processor. The operating system was called Nugget OS, which you can find copies online, but it's not exactly what's in the chip, but it's just based on that. If you look in the firmware, you see the file names brick and chunk in the version strings. The firmware itself, you can, if you download the Pixel firmware, you have to unpack it a bit until you get to the vendor image, and in this vendor image there's an ec.bin file which contains the ARM code. Quark's lab, they did some research on that specific chip. This is a picture of the phone. Not sure if you can see it, but in the middle up there, there's an arrow to the Titan chip. So this is the PCB from the Pixel 3. Then the M2, it was introduced in 21. It's codenamed Dauntless, and it's based on a RISC-V IP core from a company named Soteria. It's still the same Nugget OS. Also, if you unpack the firmware, you have to get to the same. You have to first unpack the zip file, and then there's a vendor image which you can unpack again, and then you find several ec.bin files. This is a picture of the Pixel 6 mainboard. It's the yellow chips sort of in the middle on the top. So these are not very big chips, these are just tiny chips. There's another picture showing you a coin with these two chips. So it's not like a big CPU or anything, just very tiny chips, but it adds a lot of value to the phone. The things, the specific hardware that are unique to this Titan chip, there's a Bignum accelerator, specifically for elliptic curve and RSA calculations. There's some AES crypto hardware, a random number generator, and whatever the usual microcontroller stuff that you see in all small chips. Some anti-tampering, probably. I have not taken the chip itself apart, so I don't know, just assumption, but I'm quite sure there's some anti-tampering hardware in there. Then I looked at where does Google does publish a lot of CVEs, and some of them do mention the, is it again? Yeah. The TitanM. What I noticed about this, that it's not always TitanM that they say. Sometimes they say GSC, which is Google security chip. And the other notable thing is that from 2019 to 2022, there were lots of CVEs, and then suddenly it stopped. There were just a few in 23, and then a few in 24, and only one in 25. And I did see code changes in all those times, so even though there's no CVEs anymore, Google does change the code from the chip. So maybe they're not publishing it anymore, or they think all the bugs are fixed. That's something that I thought was notable. Then the firmware. How do you get even the firmware? Before you want to analyze it, you need to download these images. The main place to get it is from Google itself. But I also thought maybe you can get old versions that are no longer published by Google. So I wrote kind of a little scraper tool to get this from the index from archive.org. And there are actually quite a lot of firmware files also, or links to firmware files that you can find on archive.org. It's useful sometimes for your research to go back into the index from archive. Then I ran into another problem. There's quite a lot of firmware, and I wanted to look through all of them to find like a complete set of all the binaries. So something that I did, you can do specify that you want to download only a specific section of a file from a URL. I wrote some tools for that, which you can find on my GitHub, to minimize the number of data that I needed to download, because I only actually needed this vendor image part of that. So I wrote there, it's about 3,000 different firmware files, and I went through all of them, and in a total, I found about 40 versions of each of the Titan firmware chip firmwares, different versions. When extracting the firmware, the zip file itself, that's probably everybody can unpack a zip file, but then you run into all these different file systems. There are Android sparse images, some are X4, some are tar files, and you can use a lot of separate tools for that, but 7-zip, that's a really handy tool for reverse engineering, because it actually understands most of these different file formats out of the box, so you don't need to mount anything or do anything difficult. You just use 7-zip and you unpack all the firmware using just that tool. This is a listing of the specific files that you will find in a Pixel 6 firmware file. Then from the operating system point of view, how is it actually used? This is when the phone boots. There's some process called Citadel Updater. This loads the firmware files from this firmware directory and sends it to the Titan chip. Then there are some libraries. There's an SPI channel through which it talks to the chip, and then there are these android.hardware.something libraries which have a GNI interface, so they can actually be used from the Java code from Android. I didn't dive too deep into that part of the software actually, but then I looked at the firmware file itself. I usually just start with a hex dump and you see immediately lots of structure because there are sections and some things look like signatures and things look like code. Well, to me, they look like obvious code, maybe not to everybody. There are two parts in it, because whenever you update the flash in the chip, you want to be sure that that's the correct one, and you want to be able to switch back to the other one. So they use an upper and a lower part of the flash chip for the current active version. There's a small loader, and then there's the main part of the code. Oh, and there's a signature, which I have not figured out yet how it works. The key looks, I tried factoring the big number, and I couldn't factor it, so I assume it's an RSA modulus. But yeah, I couldn't validate. Normally, I can just calculate, and I see an RSA key, and I want to know what does it match with, and there's supposed to be a hash somewhere that rolls out of it, but I could not find it for this firmware file. Then I wanted to disassemble and actually decompile. First I tried IDA. Unfortunately, this was IDA 8, which I tried it with. And you see there's some problem. After not so far, it already starts not recognizing the bytes. So there was something not supported by the IDA disassembler, maybe the RISC-V disassembler. This is a better detail of the same thing. Also, in IDA 9, there's now a decompiler for RISC-V, but in IDA 8, there was not yet. It was not yet there. So with IDA, I could not get very far in reverse engineering this. So I went to Ghidra. It shows the same problem. Also, lots of undefined bytes which it couldn't disassemble, but there's another, it does have a decompiler, Ghidra. Even though there are bad instructions, it just tries to at least generate some C code for you. And Ghidra has another nice feature, which I will get to, because first, Ghidra allows you to define your own processors, and it's very easy to extend the processors. So what I did, I was looking at all the words that Ghidra was not able to disassemble properly, and try to see some structure in there. So the bit patterns, I looked for the RISC-V instruction set, how is this usually encoded. There's the specification, it's on GitHub. The RISC-V opcodes repository, and it's relatively readable because it just gives you ranges of bits and the meaning. So these values like IMM20, that's specified as somewhere Oh, I didn't write it down here. It's probably the last 20 bits of the D word. I'm not quite sure because I didn't write that down. I don't remember the exact details. But then I try to match that with the unknown opcodes that I found. And I'm thinking this must be immediate, this must be a register, and some other part of the things must be then a function code or so. So what I did, I created some dummy instructions. This is what the specification language from Ghidra looks like. And I call these instructions Google 0, Google 1, and Google 2, and Google 3. Because I had no clue what they were, and I just put these bit patterns in there. And then use get the code completely disassembles, and you get your Google 0 as an unknown function, basically, in your decompilation. So then, next, I try to figure out what's going in and out, because you see there, it's using something from the CSR read function before it, and then the result is doing something, and then I had about 50 functions or so where I could look at that. At some point, I took this Nugget OS, the scheduler, because I did have source code for that, and I tried to match it up because I did notice where the scheduler was, and then I figured out, this must be a bit scan, because it was trying to match active processes in a slot of bits. So these instructions, they're actually quite simple. There's nothing magic about these instructions. This is what I found after several days of just staring at the disassembly and figuring out what these unknown instructions must do. So there were a byte swap, gets the R bit scan. It has these things have better names, but these are just invented by me. In the RISC-V standard, this is what it now looks like with my new instructions. So then it becomes clear, and all the code is now readable. I did look at the RISC-V standard, and I was wondering, but this count leading 0, it does exactly what this instruction does. But it's an entirely different encoding, and it's in a different part of the RISC-V instruction set. And you can kind of get a clue why that happened, because this was only specified for RISC-V in November 2020, and Google released the Pixel 6 in the summer of 21. So I'm guessing this just overlapped the development process. They probably just started designing this chip before November, before this specification was finalized from RISC-V. So now I had a much better idea what everything was doing. In this Nugget OS, you have apps and tasks. So it's like a regular real-time operating system that you find in many small chips. There's 5 apps, the AVB, that is the Android verified boot. The GFA was the face authentication identity, which I think stores keys. I'm not quite sure, and then didn't look that one up. Keymaster, which manages your crypto keys for you. Nugget is the basic operating system, and the Weaver is the part that manages your PIN codes for you. So you can only retry 3 times or something, and there are timeouts and all other things. And then there are several corresponding tasks. This crypto task is not part of the direct API, but it's just used by all the other applications. The chip, it talks with the rest of the operating system via some protobuf packets. And I can find all the compiled protobuf encoding in the firmware. And it's also actually, it matches quite nicely what I find online also. There's in Google source, there's a repository which has these specific protocols. Then inside the chip, there are several security levels. So there's a Cisco-like interface for these applications to call specific crypto functions, for instance. Then I ran into I saw some places which were not crypto keys, not prime numbers or whatever. They looked like something else. And this is what I looked into next. It kind of looks like this in the hex dump. And this turned out to be the code for the elliptic curve accelerator. There's something interesting about it. This is a plot from the code size, from the firmware over time. You see that suddenly it just drops quite a bit. And this is the moment that Google decided they don't use this anymore, because apparently there must have been some security bug in there, which was not, no, it doesn't match any of the CVEs, but I did notice that at some point they stopped using this coprocessor entirely. But still, I find it an interesting chip, interesting coprocessor. So I did look into what actually it's doing and how it works. This is the C code from RISC-V, where you see how it's actually calling this. It's copying coordinates to a specific memory location. Then it's calling this with, looks like a magic number, there's 0x2cc, and that turns out to be the address in the coprocessor that it's jumping to. On the right, you see the function, how it actually calls this coprocessor. There's some I/O space where some status bits are checked, and it puts the function name there, and then it waits for the status bits to change again, and then after that it copies back the results. This is a part of the coprocessor where I started seeing some patterns, because I recognize these numbers. They're exactly the generator point for the elliptic curve that was used for the ECC signatures. So since all the half of the words are parts of these coordinates, I'm assuming that the rest is probably an immediate load. And I can figure out what the bits mean, because I know the order of the things are. So by looking at this hex dump in this way, I can kind of figure out what some of the instructions are. Like there's also, is there more below there? Oh yeah, there's a call instruction, this is just 08, and then this address, because these addresses match exactly with the useful structure. And there's this return, which I assume is return, which is for very often just at exactly the right places. So I figured out I didn't write more about this coprocessor here, but I did figure out some of the instructions, but not all of it. Then the next thing I did, after looking at the firmware for a long time, and now I kind of know what it does, and I also wanted to see if I can just run it and simulate it, and maybe even find bugs in it by fuzzing it. I haven't actually done the fuzzing, but I did write a simulator. First, I started in Python. One of the things I noticed about the RISC-V processor it's such a small instruction set that it's actually just a few hundred lines of Python to get your basic simulator running. So my simulator, sorry? Oh. My simulator has a lot of these logics about I/O ports, where one I/O port needs to behave in a certain way. I have no clue what the I/O port does. I just make sure the code takes the most logic path through the code. Then my simulator is able to get the same output as I get from the debugger. There's a debugger in the Pixel phone where you can get output of various chips, and I was quite happy that it looks exactly, it runs until the idle loop, so I'm not able to talk. I didn't implement any of the SPI channel stuff yet. But it does boot the entire chip, initialize all its I/O, which doesn't exist in my simulator, but I kind of know now where it writes all these things. And then it says, task idle starting. So yeah, I'm quite happy that this simulator works. This is a special USB cable that you can make yourself. There are 2 pins, and this is where the debug output comes from USB-C. And you have to be careful with the voltage level. It's 1.8 volts, so don't put 5 there, so that will break your phone. I have some, yeah. These are the details on how to actually enable this in Android. You have to go through some steps. And this is the end of my talk. So.
Nice. I've tried Ghidra myself a bit, so I can only imagine how long this took you. How long did it take you?
I did this over several, not all at once. So yeah, but I remember this staring at these bits and trying to make sense of the unknown instructions. That's actually, I like that, enjoy this experience that you figure it out. And the same with this, yeah.
You guys are smart. You've already queued up at the microphones. But still, I have to repeat it. If you have questions, please queue up at the microphones. Thank you. So, first question, microphone 3, please.
Yeah, thanks for the talk. It's really cool. So would you say the majority of the time is looking at the static disassembly, or rather kind of trying to write tools, or maybe trying like a live reverse engineering in a simulator?
That's actually the next thing that I want to do is make sure that I get all these protobuf protocols that is running over this SPI port. I want to get that to work in the simulator so I can actually fuzz it maybe. It's very slow, so it's not that it's a very efficient fuzzing, but oh, there's another simulator called Spike, and I did implement it there as well, and that's written in C, so it's much faster. But yeah, most of my time I spent static, just looking at disassemblies, but I can run the code, and I did try, do an RSA encryption and the elliptic curve stuff, and I know that it works in my simulator.
Nice. Question from microphone number 2, please.
Yes, so did you use any, when you're comparing different versions of this firmware, did you use any like binary diffing tools, or like why or why not?
I mostly use strings, actually.
Nice.
And I just did my main reverse engineering work on just the first binary I happened to look at, and then I did notice that some code disappeared in other binaries, like this, all this elliptic curve hardware driver that disappeared and is now only all implemented in software on the RISC-V side.
Thank you.
We have a question from the internet.
Yes, the internet asks, how does it send debug output? Via same UART as Android Linux?
I don't actually know how the debug output ends up, but it's there's a mux. You can specify a mux and you can select which chip you want to talk to. So I think there's a separate channel and it's just a regular UART. Because also this UART is not visible from inside. I think there is a way to get it in the Pixel. But the easiest way is to get it on these 2 pins on your USB-C port. And you first have to boot into fuzz boot and then set all this. Did I put it on the screen? This, where this OEM UART enable and debug UART mux. With that, you can configure this special debug port.
Nice. Question from microphone number 3, please.
Thanks, it was a really great talk. Perhaps my question is a bit simple for you, but for me it's a new thing. What you showed to us was very hard work because you had to figure out the then unknown RISC opcodes and what they do, these instructions. But in general, there was no obfuscation, right? And no attempt to protect you from inspecting the source or to kind of hide it from some use. So is this normal? Was it expected that there is no additional layer obfuscation, or is this, what do you think about that?
When they obfuscate things, then they would obfuscate the entire firmware. That also happens when you have an encrypted binary and it's very hard to find the keys to it. But in this case, there was no attempt at all at obfuscation. Initially, I figured, oh, these must be magic Google crypto hardware instructions, but it was nothing like that. It was very mundane bit fiddling instructions.
Yeah, thank you.
Number 4, please.
Thank you for your talk. I didn't get one part. How did you identify from the unknown blobs that it was the ECC optimization function?
Because I saw these the coordinates, the x and y coordinate, that are from the parameters to these public curves. You can just look them up, and if you look at the hex dump, there's also the prime number it's using for the point calculations and the group, what do you call it, the group order of the curve. These are all in there. So I just recognized these constants, and I started from there, and then I figured out, these other magic numbers, they must be offsets. And what I did not yet figure out, for instance, I know some of the instructions are branches, but I cannot yet figure out when they branch forward and when they branch backward, because there seems to be no logic to that yet to me. But that's because I didn't look at it long enough yet.
Thank you.
Number 1, please.
Thank you for hardly looking into the details. I have a bit further looking question. So I have a Pixel 9 and I tried already Graphene OS. So Google is permissive, you can do a lot. But my question is, do you believe by the re-engineering you are doing that you could convince even the Pixel under Graphene OS that still credit card operations are possible? Is this a way? Can we do it? Should we do it?
The credit card operations on the phone?
Yeah, exactly. You cannot. You have to somehow compromise the security chip to convince the security chip under Graphene OS that it still believes it's under a Mint OS.
Well, I cannot put any new firmware in this because this is all signed by Google with a signing algorithm which I have not even figured out how it works, and I don't know Google's keys. So this security chip is definitely, I'm unable to put my own firmware in there yet. Maybe at some point I find some code execution, then I would probably get very rich as well, because Google puts $1 million on the bug bounty for that. But yeah, not there yet.
Don't be shy, we still have a bit of time. Question from microphone number 3, please.
Yeah, hey Willem, thank you very much for the talk. Really appreciate you open sourcing all of your tooling. That's very nice. I believe in 2022 at Black Hat US, one of the Google Red teams already demonstrated like a code execution vulnerability inside of the Google TitanM2. And it's kind of a follow-up question to the one asked before. Did you look into rollback prevention of these binary blobs that I eventually deployed on the TitanM2 chip?
No, I didn't look into it.
So I'm wondering if there's some sort of rollback prevention, or like if not, if we could just get code execution on there to figure out these custom instructions. This would have been like the dynamic way.
There is a version in there, but no, yeah. So I didn't look into that. I also don't. This is part of the boot ROM of the Titan chip, which does the signature verification, and just don't have access to that because I have no code execution on the chip.
Okay, cool. Thank you.
So if people have more questions later, how can they reach you?
It was on the last slide, or either through my GitHub or my email. Is it there? Yeah, my email is there.
Nice. So, if there are no more questions, then big applause, please, for Willem.